This is our second video in our Lay's Linear Algebra series, and as always you can find that final review packet in the description below, link to that of course. So our concept this time will be matrix algebra, which is our second concept. This will be going over chapters 2, chapters 3.1 to 3.3, and chapter 4.9, okay? So let's start off today, as always, with a quick warm-up. So the question says, given the Markov chain A, represented by the matrix 1, 0.5, 0, 0.5, determine the steady state vector Q. Well, we'll discuss more about what this means later on, but let's go through the steps to do this through our warm-up. Okay, the first thing that we're going to do is we know that AQ is equal to Q for the steady state vector. Now, because we know that AQ is equal to Q, we know that AQ minus Q is equal to 0. Q is just I times Q, and we can say that I is the identity matrix between A that has the same dimension as A, which is also a square matrix. So then we have A minus I, and then Q is equal to 0. And so then we can just set this up through our augmentation. A minus I, 0, Q. We can find Q through our augmented matrix as such. So let's do the following. So let us go through those steps. So our identity matrix is going to be 1 on the diagonal. So we're going to get 1 minus 1, 0, 0.5 minus 0, 0 minus 0, 0.5 minus 1. That's going to give us negative 0.5. We've augmented that with 0, 0. Okay? And now we can add this to that. We get 0, 1, 0, 0, 0, 0. Alright. So what we get is x2 is equal to 0, and x1 is equal to free. x1 is free. Alright, so since x1 is free, what we get is q is equal to q1, q2, because we're in the second dimension. And so then this is equal to, q1 we know is something as x1 in our case. So that's going to be free, so we can just say that's q1. q2 is 0. And so what we do is we take out q1, we get 1, 0, and then we divide by the sum of all the numbers of all of the values within the vector. And since that's just 1, we're going to get the same thing. And so our steady state vector is 1, 0. And we can plug this back in to check. So if I say that Q is 1, 0, then if I multiply this by 1, 0, I should get 1, 0, because that's what the steady state means. Let's try it out. So if I do this, then I get 1. And if I do this, then I get 0. And so therefore, this is in fact the steady state matrix, the steady state vector for this Markov chain. So our first guided question is, what is the transpose of a matrix? Well, essentially the transpose of a matrix is where we swap the rows and columns. If I have A equal to 1, 2, 3, 4, then the transpose of A is going to be to make this row the column, so then we get 1, 2, make this row the next column, 3, 4. The next one is, how do you determine the determinant of a square matrix? Is it possible to find the determinant of a non-square matrix? Well, the answer to the second question is easy. No, you can't find the determinant of a square matrix because it in fact is impossible to get the determinant through it. How do we find the determinant of a square matrix? Well, we'll refer to our 2x2 matrix A. Okay, A, B, C, and D, alright? Now, what we need to do from here is to find the determinant of a 2x2 matrix. It's relatively simple. Just do AD minus BC. Now it gets a little more complicated when you get into higher dimensional matrices. So what we use is we use the cofactor method. So if I have A, which is in R to the 3 by 3, and then A is A, B, C, D, E, F, G, H, I. Okay? then what I do is I write plus, minus, plus, and then I continue doing that for any higher dimension. Alright, now what I do is, for this one, I ignore anything that is in the same row and same column as that first element in the row. Anything that is in the same column, same row, ignore, okay? And then multiply it by positive or negative 1. So what we're starting off with positive a, alright? And then we multiply it by the determinant of this submatrix here. And so we know that that's going to be EI minus HF. Okay, then we have minus D, okay, because that's minus D, times, and that's going to be, well, we're ignoring this, this, and this, so we're only looking at B, C, H, and I. So that's going to be BI minus HC. And then the next one is we're just going to be adding G times, we're ignoring this row and this column, and so we get B, we're ignoring this row and this column, so we get BF minus EC. And so then that is our cofactoring method. You just take the determinant of the submatrix and multiply it by the coefficient, which is the first element in the first column, and then multiply it by either positive 1 or negative 1, depending on whether it's the odd row or an even row. The next question is, what are the rules for invertibility? Now, there are a lot of rules for invertibility. One of them is that you need to have a non-zero determinant for a square matrix. Now, only square matrices can be invertible. Now, what does invertibility necessarily mean? Well, say we have the matrix A, which is A, B, C, D. Okay, so that's in our the 2x2. Okay, so this is in our 2x2 real space. So what we're saying is that when we this matrix is invertible, we're saying A to the negative 1 has a value. So what does the inverse do? Well, it's just saying that A times A inverse is equal to the identity matrix, but then also A inverse times A is also equal to the identity matrix. So if A is not necessarily in the 2x2, say A is in R to the n by n, then this is just going to be the n by n identity matrix. Okay, so that's what the inverse matrix is. Now we will learn in pre-calculus that the inverse, that we don't divide by matrices. So if we have AX equals B, you don't solve it by doing x is equal to B divided by A. No. You solve it by doing x is equal to, and this is going to be A inverse times B. Alright? Or you can solve it through, of course, our augmentation method. But I digress. Let's move on to our next question. What are the properties of matrix operations? Well, one thing that is very important to know is that matrices are non-commutative. Well, most matrices are non-commutative. There are some that are commutative, but those are special cases. Since not all matrices are commutative, it is safe to assume that matrices are not, by definition, commutative. And I think that's the most important matrix operation that you need to know. Other than multiplying, when you multiply two matrices, you multiply row by column, but that's a pre-calculus thing, and you can actually take a look at all of those matrix operations in the pre-calculus section of my website. How do I determine the inverse of a matrix more easily than cofactoring and utilizing adjunct matrices? You don't need to know what any of that means. You don't need to know what an adjunct matrix is. You do need to know what cofactoring is, and we just went over it. However, you definitely do not need to know how to find the adjunct matrix, because that is a more advanced topic. And honestly, that takes way too long, and lazy linear algebra is fast. So what we're going to do is we're going to take a matrix A, and then all we're doing is we're going to augment it. Well, first of all, I need to define A in the space. So A exists within our n by n real space. Okay? We can find the inverse of A by augmenting it with the n by n identity matrix. And if we end up with, after doing row reduction, we end up with this, if it has an inverse. If it does not have an inverse, then we will not get the identity matrix if it does not have an inverse. And therefore, we know that it is non-invertible. is it possible to have a singular, non-invertible elementary matrix? Quick answer, no. Now, how do I know this? Well, an elementary matrix is just when we take the identity matrix and we perform one row operation on it. One of the elementary row operations that I discussed in the previous video. Now, there is no possible way of taking the identity matrix and then using a row operation to get a non-invertible matrix. And I want you to understand that you cannot multiply a row by the scalar value of 0, because what that does is if you, for multiplying by a scalar, not row addition, you can do multiply by 0 in row addition, but you can definitely not do, you can multiply by a 0 to the one that you're adding, but not to the one that you currently have. Never. You can never multiply it by another one. Now, the reason for this is because if you multiply by 0, you're changing the actual space of the matrix, and that changes the determinant of the matrix. So, basically, there is no possible way to do that. Now, you can get a negative determinant if you do a row swap. So, if I have the identity matrix and then I do a row swap between the top and bottom rows, then what will be the determinant of this matrix? Well, it's actually going to be, instead of 1, which it is for the identity matrix, the determinant of it is going to be -1. And how do I know? Well, it's going to be 0, -1, -1. And so essentially what you know is that you can determine the determinant based on the number of row swaps, because if it's just after reducing to the echelon form where the determinants are pretty much on the line, right? The determinants are on the triangular matrix. Now, once we get that, we pretty much just multiply that value by the number of row swaps. So if the number of row swaps is, by the number of row swaps times -1. So it's -1 to the power of n, where n represents the number of row swaps. Or we can say -1 to the power of r, where r represents the number of row swaps. And then multiply that by the original determinant of A to determine your new determinant. That's a lot of determining. Now, the next question is, what is a partition matrix and how is it useful? Well, a partition matrix is useful because it allows you to represent a matrix by breaking it down into different parts. So like if I have the three-dimensional rotational matrix, cosine, phi, negative sine, phi, sine, phi, cosine, phi, 0, 0, 1, 0, 0, like this. Well, then I can just represent that through a partition matrix, where I say that R is our two-dimensional rotation matrix, and then I just say, well, this is a 0, 0, this is a 0 vector, this is a 0 vector, and then here we just say, well, that's 1. There you go, just like that. That is the partition matrix. It's just breaking down a matrix into sub-matrices, and you actually use partition matrices when doing the cofactor expansion for the determinant. Now, how do you determine the LU factorization for a matrix? Now, the LU factorization is where you use L, which is a lower triangular, and U, which is a echelon form of A. So if we have A, then that's equal to LU. So the first thing we need to do is we need to find U. Just reduce it to the echelon form, and then we do the inverse and negative of those row operations that were performed, and we perform that on the identity matrix that exists within the same dimension as A. So A can also just be non-zero as well, okay? So we do that to the identity matrix that exists within the same dimension as that. So like if A is a 3×2 matrix, then L is going to be a 3×3, and U is going to be a, well, what's the dimension of this? Well, this is 3×2, so it's going to maintain that 3×2 dimension. And so multiplying those two matrices together, it's going to get to your your A matrix, because it's a 3x2 dimension, because the matrix multiplication. Again, you can see that in the pre-calculus section of my website. The next question is, what are the unique properties of a triangular matrix? Pretty simple. The triangular matrix, normally if you multiply the values on the main diagonal of a triangular matrix, you will get the determinant. That's how you find the determinant. And so that's why the determinant of the identity matrix is 1, because 1 times 1 is 1. Now this only works for triangular matrices. The next question is, what are some examples of Leontief input-output model? Of the Leontief input-output model. Well, the Leontief input-output model is just the model of an economy broken down into sectors. And then the number of inputs and outputs are modeled through a matrix. And that's pretty much what you need to know for the Leontief input-output model. There's actually going to be a sample question that we're going to get into, and that'll help visualize it a little bit more. And the matrix that represents that input-output is known as the consumption matrix, or C. What are homogeneous coordinates, and how are they used? A homogeneous coordinate is just a coordinate that represents a system, so that you're dividing each coordinate by the same value. So if you have x, y, and z, the homogeneous coordinates would be x over h, y over h, and z over h, like that. That brings it to its minimal value. Right? That's pretty much what they are. And how are they used? Well, they're normally used in like three-dimensional rotation matrices and things like that. Matrices where you can use them to represent different things. What is a subspace, and how does it relate to span? A subspace is essentially, let's model this with an example. Then a subspace would be anything that exists maybe here, and the 0. A subspace is basically just a space that exists within another space. Now, the entire space itself is the space itself is a subspace of itself. Right? So a subspace is just some space that exists within a certain dimensional space, and it has to include the 0 matrix, and the two matrices and all of the vectors have to be written as a linear combination of some basis vectors, and so that's why it relates to span. So basis means that, remember how I talked about I hat and j hat in the last video, right? Well, I hat and j hat are the basis vectors for your two-dimensional space. Now, that means that if I can represent this subspace here with two vectors, maybe u and, I don't know, say w, then that is a subspace. Now, a subspace can also just be a line. This is the subspace, represented by a vector u. So this is the base. So this subspace is spanned by the vector u, and so therefore we say that our basis is just the vector u. So a basis is just a vector that models the span, a vector that exists within the span of a space or a subspace. And remember that a space can be a subspace of itself. The next one is define dimension and rank. What is their purpose? What is the validity of the rank nullity theorem? Well, if I have an m by n matrix, right? The rank is the number of independent, linearly independent, columns in A. That's the rank of A. And then the nullity of A is just the number of dependent columns in A. Or you could say that this is the number of pivotal columns, and this is the number of non-pivotal columns. And therefore, the rank nullity theorem states that the rank of A plus the nullity of A is equal to n, the number of columns in A. Now, what is dimension? Dimension is just the dimension of a space. So, again, if I have two linearly, so if I take this basis, which is like this, right? So this is our basis for some subspace or some space. Then what this means, when I say dimension, is that dimension is the number of vectors that exists within that basis. Now, if I add, say, the 0 matrix here, what is the dimension? If I add the 0 vector here to this basis, what happens to my dimension? It doesn't change because this is dependent. It's the number of independent vectors within the basis. And a basis should be made up of only linearly independent vectors anyways, because that is the definition of the basis. How does rank apply to the invertible matrix theorem? If you have a rank of n, which means that you have n pivotal columns, which means all of your columns are pivotal, then the matrix is invertible. That's what rank tells us about invertibility. So if the rank is less than the number of columns, then you know that the matrix is non-invertible or singular. How can I determine the null space and column space of a matrix? That is an excellent question that we're going to have to go through together. So if I take the matrix 1, 2, 5, 7. All right. How do I determine the, actually, let's make this a little bit longer. So then we'll make this 2 and then 10. No, sorry. How about 3 and 12? 3, 12. All right. This is our matrix A. Let's determine the column space and the null space, and we'll represent them through the basis of the subspaces. Now, the column space and the null space are just the subspaces of this matrix, okay? They're the subspaces that exist within the R to the n space, right? So they exist within R to the n, and they form a basis for a subspace of R to the n. So they can form a basis, so they can be R to the n. They can form a basis for R to the n. Like the identity matrix, the column space is represented through the matrix, the vectors in the identity matrix, which is I hat and j hat, and therefore the column space is since it's a subspace of R squared, is going to be the subspace of itself, and that's how you prove that space can be a subspace of itself. Alright, and so let's just, what we're going to do to find the column space is we bring it to the echelon form. Not the row-reduced echelon form, the echelon form. Then we take those pivotal columns, and those columns that are pivotal, we go back to the original matrix, we take those columns before they were reduced, and then those form the basis for our column space. So if I reduce this to echelon form, then I get, well, I'll do 5, 10, 5, 7, negative 5, negative 10, my bad. Multiplying by negative 5, so it's going to be negative 15. And then it's going to be 12. Alright. Then the next thing is going to be, we're going to just add this to that. And so we get 0, we'll multiply everything here by negative 1/3, so then we get negative 1/5, my bad. 1, 2, and 3. 7 minus 10 is going to be negative 3. 12 minus 5 is going to be negative 3. Alright, so then that reduces to 1, 1. Alright, but then I can make that 2, 2. Okay, subtract that from there. Then we get 0, negative 1, which reduces to 1. As such, 3, 1, like this. And then what happens is that we just subtract this by 3 times that, and so we get 0 there. Now, I know, this is the row-reduced echelon form, but it technically doesn't matter as long as it's in an echelon form. It can be the row-reduced, or it can be the echelon. You technically don't need to go to the row-reduced, you just need to get to the echelon form so that you can obtain the pivotal columns. but it just so happened that while I was trying to get this into echelon form, I ended up with the row reduced echelon form, but that is completely fine. So here are our pivotal columns right here, the first and the third. So if we go back here, then that will form the basis for our column space. So our column space of A can be represented through the basis of 1, 5, and 3, 12, which can technically be reduced to 1, 4, but we'll leave it as 3, 12. All right. Next step is to find the basis for the null space of the same matrix. So we have 1, 3, 2, then we have 5, 7, 12. All right, so now we go back to our row reduced echelon form, but first we need to actually augment this with the zero vector. All right, since when we augment with the zero vector, we know that once we get to row reduced echelon form, we're going to get the zero vector in the augmentation as well. So since we already know that this is our row reduced echelon form, we just augment that with the zero vector. Now that we've augmented it, we know that x1 plus x2 is equal to 0, so we know that x1 is equal to negative 2x2, okay, because this is x1 plus 2x2 is equal to 0, plus 0x3, of course. And then we have 0x1 plus 0x2 plus 1x3 is equal to 0, so we get x3 is equal to 0. And so now if we plug that into x, which is just x1, x2, and x3, then we get, well, this is negative 2x2, x2, and then x3 is 0. Alright? And then we can just take out x2. We're left with negative 2, 1, and 0. And so we only have, so then we take this vector that we got, and then that forms the basis for the null space of A. Just that one. And as you can see, the dimension of the column space was 2, and the dimension of the null space is 1. 2 plus 1 is 3, and that's the number of columns that we have in our matrix A. The next question is, what is a basis? We've already discussed that. We're moving on. How do I construct a Markov chain, and what is a steady state vector? Now, we're actually going to describe this a little bit. We're actually going to get into that right now, okay? So the Markov chain, like we did for the warm-up, is just a representation of probability, or just some sort of chain. Each column has to add up to 1. So every element in the column. So we had 1, 0, 0.5, and 0.5. As you can see, these both add up to 1. So one thing you need to know is that the Markov chain has an that the matrix representing the Markov chain, okay, so this one, will always have an eigenvalue of 1. What does this mean? Well, it just means that when we do A times X, there's a possibility that we will be returned with X, because our eigenvalue is 1. So here's how eigenvalues work. We get Ax is equal to the eigenvalue represented through lambda times x. So it just multiplies it by some value. Now, they can be complex because there's a difference between a complex and a real eigenvalue, but we'll discuss that later. A complex eigenvalue is just a rotation in the plane, while a real eigenvalue is a stretch in the plane. All right? And all we need to know is that this is just an eigenvalue of 1 because we get Ax equals x, and that's how we did before when we said Aq was equal to q. Suppose A, B, and C are n by n non-zero matrices. If A times B minus C equals the n by n zero matrix, then B is equal to C. This is false. The reason why this is false is because B does not necessarily have to equal C, nor for two matrices, say the difference between B and C, times A to give you the zero matrix. They just don't necessarily need to be square, because most of the time when you think about matrices, you think about it in the terms of a square matrix. Okay? They don't need to be that. Now, it is impossible to have two matrices A and B, both of which are 2 by 2 and non-zero, whose product AB results in the 2 by 2 zero matrix. This is also false. Remember I said that you could think about it in terms of the square, non-square? Well, I lied. They don't necessarily have to be non-square. They can be square as well. They just need to be what is known as orthogonal. When you take A and you multiply it by B, if those two matrices are orthogonal to each other, then when you multiply them together, you should get 0. And the way that you know that is because, we'll say A is equal to the transpose of itself, and then B is the, and we'll get more into that in maybe 2 videos down the line, because that deals with orthogonality, which is just perpendicular and stuff like that. But I digress. We'll move on from there. That's just the reasoning as to why that is false. There's probably a better reasoning that I might not know, but that's how I understand it. So just know that that is false. You can have two matrices that are square that multiply together that give you the zero matrix that aren't necessarily the zero matrix themselves. Number 3 is if a square matrix is not invertible, then it does not have an LU factorization. False, because invertibility has nothing to do with the LU factorization. When I was discussing LU factorization, did I mention anything about invertibility? No, so this is false. It has nothing to do with invertibility. The next one is if H is that H is equal to x in R squared, x1 plus x2 is equal to 1, is a subspace. Now remember, a subspace has to have some sort of basis, right? Has to have some sort of basis. The vector needs to have a basis where the vectors in the said basis exist within the overall space, and that it needs to include the zero matrix, the zero vector, okay? So, the question says that H is equal to x in R squared, okay? And then it says x1 plus x2 is equal to 1. So it says that this is a subspace. So the way to prove it is to find the space. So we know x1 plus x2 is equal to 1. So x1 is equal to 1 minus x2. Now x is equal to x1 and x2 because we know that it exists within R squared, so it only has two elements in the vector. So this is going to be equal to 1 minus x2, x2. So now if I split that up, then I get 0 plus x2 here, so then I'm going to get 1, 0. Then that's going to be plus negative x2, x2. Then I can take out x2 from that one. From that one, and I get negative 1 and 1. What do you notice here? Well, no matter what value of x2 I plug in here, we'll never get the zero. We'll never get the zero vector. Why? Well, if x2 is 0, then we still get 1 here, and we'll never get the zero vector. Okay? And that is the problem. Is the fact that we'll never get the zero vector from here. Therefore, that question, number 4, is false as well. Because in order to be considered a subspace, it needs to have the zero vector exist within said subspace. Alright. Next question, number 5. If ax equals ay for some x does not equal y, then a cannot be invertible. This is true. Obviously true. If ax is equal to ay and x does not equal y, then we cannot say that x is equal to y, because if a is invertible, then that would be a inverse times a times y. This gives us the identity matrix times y, which just gives us y, so this would be saying that x equals y. But that contradicts this, and so therefore we know that a cannot be invertible. So since it cannot be invertible, that means that this would be true. Alright. Next question, number 6. If a is non-singular, then a to the n must be non-singular for any integer n greater than 1. Well, let's take a non-singular, which just means invertible matrix. We'll say, take this matrix. We know that this is invertible because it has a non-zero determinant, 4. That non-zero determinant is 4, right? So if I take this to the power of 2, then that's just going to be this times itself. So this only works with square matrices, and therefore you can't do this with singular matrices, right? You can't do a to the n if a is non-square. So it would have to be a singular square matrix. Okay. This is just going to give us 2 times 0 times 2 times 1, which is just going to give us 4. This is going to give us 4, 0, and then 1. Alright, so that's what this is equal to. Again, now this is the diagonal matrix, a triangular matrix. When you have a triangular matrix, when you take it to the power of some number, it's just going to be the diagonal to the power of said power. We'll get more into that next video probably. But yeah, so that's how diagonal matrices work. We'll discuss more about that when we talk about diagonalization. Now, this matrix is also invertible. Now again, you could probably come up with some counterexample. This is a relatively small one. I can do a bunch of different things, but if you think about it, if two matrices are invertible, when you multiply them, you should get an invertible matrix. Now, this does not apply to addition. This does not apply to matrix addition whatsoever. If I do A plus B, then just because A and B are non-singular, that does not mean that their sum is going to be non-singular. All right, let's take a look at a counterexample for that. 1, 0, 0, 1 plus, say this is negative 1, 0, 0, negative 1. These are both non-singular invertible matrices. If I add these together, I get 0, 0, 0, 0. This is a singular matrix. Therefore, this is false. You cannot add two non-singular matrices that results in a sum that will always result in a sum of non-singular matrix. Those two do not relate whatsoever. Question number 7. All elementary matrices are triangular. False. If I take the 3 by 3, identity matrix, and then I use a row operation on this, like say a row swap between the middle and bottom row, then I get 0, 0, 1, 0, 1, 0, 1, 0, 0. This is clearly not a triangular matrix, and this is still an elementary matrix, so therefore this question is also false. Number 8, if the transformation T of A has domain 3, a codomain 4, and is 1 to 1, then the rank of A is 3, and the nullity is 0. Well, we just went over the rank nullity theorem before, didn't we? We said that rank plus nullity must equal the number of columns in the matrix. Now it says it has a domain of 3 and a codomain of 4. So this, remember, is the codomain, and this is the domain. So this is 3. So since we have a 3 by 4, so we know that this would be a 4 by 3 matrix. And so therefore, since our rank is 3, and our nullity is 0. 3 plus 0 is 3. That's the number of columns we have, and therefore this is true. Now, if A is square, and also it says that it's 1 to 1, right? So since it's 1 to 1, we know that the rank has to be 3, because 1 to 1 means that it's all the columns are linearly independent, but I digress. Now, next question, number 9. If A is square and row equivalent to the identity matrix, then its determinant is non-zero. True. That pretty much is self-explanatory. Next question is if AX is equal to B, if AX equals B has exactly one solution for every B, A must be singular. It has exactly one solution for every B. If it has exactly one solution for every B, then it is definitely not singular, so this is false. In order to have exactly one solution for every B, you need to be 1 to 1. Now, you could be on 2, but you need to be 1 to 1, which means that all of the columns are linearly independent, which means that A is non-singular, not singular, all right? Number 11, if X and Y are linearly independent and in R3, then X plus Y is basis of R3. Well, let's think about it, right? If I have in R3, so remember, the number of vectors represents whether it's a subspace, the dimension. So the dimension of that has to equal whether it's a subspace of said space, all right? All right. So we have what is it? X, Y, and X plus Y. So because X plus Y is linearly dependent, this cannot form a basis for R cubed. Now, why is that? Well, because in order to be a basis for r to the 3, you need to have 3 vectors. We need 3 linearly independent vectors, which means that the dimension must be 3, but it's 2. And so therefore, this is not a basis for R3. Now, it is the basis for a subspace within R3, perhaps, but it is not a basis for R3 itself. Alright, just because you're the basis for a subspace does not mean that you're a basis for the space. Now, next question is number 12. The set of solutions to ax equals b for any real b is a subspace. The set of solutions to ax equals b for any real b is a subspace? Since when did we relate the set of solutions to ax equals b to a subspace? No. Ax equals 0 is to a subspace. But this says for any real b? No, that's definitely false. So that's false. The next one is if ab equals I, then ba equals I if both are n by n. We already discussed that earlier. Property of invertible matrices. If A and B are both n by n and share the same null space, then they have the same RREF. True, because again, the null space is related to the RREF as I showed you before. Row swap does not change the determinant. False. I discussed earlier that it does. A dimensional space is a subspace of itself. I've said this multiple times. Yes, in fact it is. A steady state vector is just a vector that exists within the eigenspace formed by an eigenvalue of 1. I discussed this as well. This is also true. The area of a parallelogram, we didn't discuss this, with vertices at 0, 0, CD, AB, and A plus C, B plus D in R squared is equal to the determinant which is just AD minus BC. This is true. The area of a parallelogram represented, where the coordinates are represented by the columns of a matrix is represented by the determinant, or the absolute value of the determinant, because the area is always positive, right? So yeah, the absolute value of the determinant will give you the area. So now we're on to our practice problems, which we didn't actually do before. These are actual practice problems. Give the consumption matrix if the economy contains 2 sectors, x and y. X requires 0.3 units. Well, let's write this down first. So we have it has 2 sectors, so we know that it's just going to be x and y like this, right? Now, x required, so this is our input, and this is our output, all right? X requires, this is the other way around. This is our output, so this is and this is our input. So this is what we need in order to output said sector of the economy. Now, x requires 0.3 units from x and 0.1 units from y. And then y requires 0 units from x and 0.2 units from y. We are done. That is our consumption matrix. Thank you very much. I'll be here all day. Next question. B and C are square matrices with determinant BC equals -2 and determinant of C is 3. What is the value of the determinant of B times the determinant of C cubed? Alright, let's write this down just so that you guys can see it, but it should be on that packet so that you guys are looking at it. So we know that the determinant of BC is equal to -2, and the determinant of C is equal to 3. So we need to find the determinant of B times the determinant of C cubed. Well, how do we determine, well, we know that when we multiply 2 matrices based on the properties of determinants, we know that the determinant of BC is just equal to the determinant of B times the determinant of C. Alright, so since this is -2, and we know that this is 3, we know that the determinant of B must be what? -2 divided by 3, which is -2/3. So then the determinant of B times the determinant of C cubed, which is just going to be the same thing as saying the determinant of C cubed, rather than the determinant of C cubed, the determinant of C cubed. I know, I'm saying the same thing, but if you look, then they're different, right? Then we know that this is 3, and this is -2/3, so what we get is we get -2/3 times 3 cubed, which is 27, this becomes 9, this becomes 1, we get -18 as our answer. Alright, next question. If the rank of a 5 by 11 matrix is 3, What is the dimension of the null space? Well, the rank is 3. The dimension of the null space is the same thing as the nullity, right? And the rank is the same thing as the dimension of the null space. The dimension of the null space is the same thing as nullity. And the dimension of the column space is the same thing as the rank. Alright? And then if the rank is 3, and we have a 5 by 11 matrix, that means we have 11 columns. So 11 minus 3 is 8. So therefore, we know the dimension of the null space has to be 8, because the rank nullity theorem. Construct a basis for a subspace that does not include the 0 vector. Well, this is a trick question. A subspace always has to include the 0 vector. Therefore, this is not possible. Trick question. Given a sample matrix, derive the basis for its call space and null space. We already did that before. We don't need to do it again. Now, determine the volume of a parallel pipette spanned by the columns of 1, 2, 3, 2, 3, negative 1, and 1, 6, 7. This is a 3 by 3 matrix. You have to find the determinant, and I'll leave this one up to you. You should be able to do it using cofactoring. It should be relatively simple. Alright, I wish you guys luck, and I'll see you in the next video.